Welcome to another edition of Functional Analysis with Will. We're going to begin with proposition 4.33. If P is a positive operator on a Hilbert space H, then there exists a unique positive operator Q such that Q squared equals P. Moreover, Q commutes with every element that P does. So to begin this, we need to show that the square root of P is in fact well defined, but this follows is well defined. But this follows directly from 4.31 and the spectral theorem 4.30. Yes? And we also know that the square root of P is also a positive operator because the spectrum of P is positive. And the square root function is continuous on the positive real numbers. Moreover, its range is in the positive real EAL numbers when its domain is restricted to the positive real numbers, which I'm now going to denote like that. Now, it might not be immediately obvious why we get that its positivity follows from this argument, but if we look back on corollary 2.37, we get that sigma of the square root of P is in fact equal to the square root of sigma of P, which then allows us to use 4.32, which is a corollary, to get the desired result. Yes? Now we know that the square root of P squared is equal to P, and this follows directly from the definition of functional calculus. As well, we get the commutativity claim from 4.31 as well. Specifically, a comment that is made in the second to last paragraph, which is, moreover, if A is an operator in H that commutes with T and T star, then T commutes with every operator in C sub T, and hence, in particular, with phi sub T, for each phi in the set of continuous functions on the spectrum of T. So, the last thing that we have to prove is uniqueness. So the way that we're going to go about proving uniqueness is by assuming the existence of a q that squares to p. Then we're going to show that the square root of p and this q have to in fact be equal. And we're going to start with a little bit of an algebraic manipulation to show that they are in fact that they commute with each other, the square root of p and q. And to do this, we're going to use our definition of q, multiply it by p, which obviously allows us to commute because everything commutes with itself, which then is going to give us that p commutes with q. And by our prior remark, we get that the square root of p must commute with q because q commutes with p. So this implies that the square root of pq equals q square root of p. Now there's a natural consequence to this, that if we take the algebra, let U be the algebra generated by p, q, and the square root of p, then U is commutative. And this should be relatively obvious. So next we're going to quickly define the Gelfand transform, which is going to go from U to C mu. And so we're going to define this guy here, and then we're going to make two remarks, so two notes. One is going to be, the first is going to be that since U is a closed self-adjoint subalgebra, we get that the spectrum with respect to U of P is equal to the spectrum in the larger space with respect to P, and the same thing for Q. And this is a direct, this is theorem 4.28. So this is going to be 4.28 is for that one. And our second remark is going to be that that the spectrum of P is equal to the range of the Gelfand transform of P, and we get the same thing for Q. And this follows from corollary 2.36. I say follows, that is corollary 2.36. And you'll notice that I dropped the subscripts on the sigmas now because we've already shown that they are equal, but these would obviously be U's, have subscript U, because that's how we've defined the Gelfand transform. Now lastly, since the Gelfand transform is a homomorphism, we can do several algebraic manipulations. So we're going to consider the Gelfand transform of the square root of P, and we're going to square the whole thing. Now, because it's a homomorphism, we can pass that squared through and end up with that this is equal to P. But P by definition is Q squared. Or by definition Q squared, that's equal to P. So we get this, which again I can transfer out. But this implies that the Gelfand transform of the square root of P is equal to the Gelfand transform of Q. So this gives us our desired result, that P is equal, or Q is equal to the square root of P as desired. So this gives us uniqueness and completes the proof.